Let's talk some more about changes of state. First of all, a liquid is considered volatile if it will evaporate rapidly. And what the diagram here shows that when the evaporation occurs, it can cause the formation of bubbles within the liquid if the vapor pressure can overcome atmospheric pressure within the liquid. And it can also result in molecules escaping the surface of the liquid and entering the surrounding atmosphere. A non-volatile liquid is a liquid that is much less likely to escape or evaporate. Volatile liquids tend to have lower boiling points, and non-volatile liquids have higher boiling points. Boiling, as I said, is when evaporation occurs throughout the liquid, not just on the surface. And the boiling point is a temperature at which a liquid will boil. Now, as it turns out, because of the difference in pressure, atmospheric pressure at altitude, at higher altitudes, the boiling point decreases with increase in altitude. And this is because the boiling point is the point at which the vapor pressure is equal to atmospheric pressure. So if atmospheric pressure changes significantly, as it would on the top of Mount Everest, then the boiling point will change. At sea level, boiling points are 100 degrees centigrade for water. And at the top of Mount Everest, the boiling point would be at 70 degrees centigrade. Now, just like the effect on the freezing point, if you add a solute to a pure solvent, it changes the boiling point. But instead of depressing the boiling point, it actually raises the boiling point by interfering with the escape of the molecules from the surface of the liquid. So the heat of vaporization is that heat that it's another form of latent heat. That is, it's a heat that occurs without changing in temperature, and it's the heat required to change a liquid into a gas without a change in temperature. So let's look at another set of problems. This time we'll look at a set of problems that look at boiling instead of melting. How much heat is needed to change 100 grams of water at 100 degrees to steam at 100 degrees? And the heat of vaporization is 2260 joules per gram. Now, if we were going to do this problem, it's the same equation, except now we change heat of formation to heat of vaporization. And so in this case, we would have 100 grams of water multiplied by 2260 joules per gram. And this is grams. And the grams cancel each other out, and you end up with 2.26 times 10 to the 5th joules. This other question says how much heat is needed to change 350 grams of lead at 1750 degrees to gaseous lead at 1750 degrees. This is the boiling point of lead. And it's the problem is done exactly the same way. Q is equal to M HV. And so M here is 350 and HV is 870. And so this is going to be equal to 3.05 times 10 to the 5th joules. So 3.05 times 10 to the 5th joules. Now when we look at these situations, here we have liquid water in a container and a closed manometer. In a closed manometer, there's no pressure here. And so any difference in this mercury manometer represents a difference in pressure inside this container. And what happens is when the liquid evaporates, the vapor pressure occurs and it causes this manometer to change. And at some point it reaches a steady state for the temperature inside this container. And whatever that steady state temperature is, that's the vapor pressure of this liquid at that of this substance at that temperature. So vapor pressure is the pressure exerted by a liquid that's in a gaseous state at a specific temperature. It depends on the type of liquid involved, the temperature, as I said, and the purity. Remember that the addition of a solute to this changes the vapor pressure, and it actually would lower the vapor pressure. Now this is what's called a heat pump, and you need to look in your book and read about how heat pumps operate. A heat pump is a device that uses mechanical energy and latent heat to transfer thermal energy from a cold location to a warm location. And what you do is you compress. The flow is this way, and the heat source transfers heat here, and then it compresses it and moves it on this side, and useful heat is lost here, and the useful heat is given up in the form of the heat of vaporization, and then it passes here and it goes back in here, and you can read this in the book, and I think it does a better job of explaining it than I can do on this video. The material that's generally used throughout this system is called a refrigerant, and it's usually selected based on favorable characteristics of its heat of vaporization. The compressor, which is right here, is a device that compresses the refrigerant to high pressures to prevent it from vaporizing. So it's a hot refrigerant that's compressed, and then it loses its compression, and as it loses its compression, it will vaporize in here and give up heat, and then it passes in here and takes on heat and then is compressed again. Here's another example of the same thing where you have the heat exchange on this side, water coming in, it takes on the heat and going out. This comes out as a hot gas. It's then compressed, and then it's going this way, I'm sorry. It's compressed, and it moves into, it goes as a liquid into this area. The heat exchange occurs, and then it comes out, and then it expands, and then it takes on ambient air at this point. So this device is where the refrigerant is cooled to room temperature. So that's on this side. And then the evaporator is the device is where it's allowed to evaporate on this side. So the heat exchange is here, and the cold exchange is here. So the use of changes of state to transfer heat is commonly used, and they use pressure to control the changes of state. Now there's one other process that can occur, and that's called sublimation. And sublimation is the transfer from solid to gas directly without a liquid phase. So here you have water, which does not sublimate. It goes to water and then to ice, or ice to water to steam. But dry ice, which is frozen carbon dioxide, it goes directly to carbon dioxide and then back to ice without a liquid phase. And disposition is when it goes from gas back to the solid.